The chemistry behind enzymes. Enzymes are biological catalysts that are used in every biochemical reaction. They are also very specific for each reaction. As we learned in a previous unit, catalysts increase the rate of a chemical reaction without being chemically changed itself. This graph shows a visual representation of a catalyst, or in this case, an enzyme. It is plotting the amount of energy throughout a reaction. The red line represents the pathway for an uncatalyzed reaction, while the blue line represents the pathway for a catalyzed reaction. As you can see, the activation energy, or the amount of energy needed for a reaction to occur, is much lower for the catalyzed reaction. The substrate, or reactants, and products, however, remain unchanged. The graph illustrated the basic definition of a catalyst or enzyme. The presence of an enzyme provides the reaction route of a lower activation energy and so enables the reaction to occur more quickly at the same temperature. Enzymes are globular proteins, which means they exist in compact spherical shapes when in aqueous solution in cells. They have a specific 3D shape, which is important for enzyme activity. They are also large molecules composed of many amino acids. The picture on the left shows the basic structure of an enzyme. The reactant in a catalyzed reaction is called a substrate. The active site, usually a pocket or a groove on the surface of the enzyme, is a small region where binding between substrate and enzyme occurs. The substrate is usually smaller so it can fit within the enzyme. The action of the enzyme comes from its ability to form a temporary binding to the substrate. There, it is held by relatively weak forces of attraction, and it forms the enzyme-substrate complex. The formation of the complex depends on the chemical fit between the substrate and the side chains of amino acids at the active site on the enzyme. The binding within the enzyme-substrate complex involves non-covalent interactions, some of which are hydrophobic interactions, dipole-dipole attractions, hydrogen bonds, and ionic attractions. The binding in the complex puts a strain on the substrate molecule, which facilitates the breaking and forming of bonds. Once the substrate has reacted, the product form no longer fits in the active site and so it detaches. The enzyme is then released unchanged and is able to catalyze other reactions. Enzymes are specific for their substrate and the reaction they catalyze, meaning an enzyme can usually only catalyze one reaction. This graph shows the concentration of substrate compared to the rate of the reaction. As the substrate concentration increases, the rate of the reaction decreases, and the enzyme becomes saturated with substrate. This shows a logarithmic relationship between the two variables. Enzyme activity can be altered by the physical and chemical environment it is placed in, such as temperature, pH, and heavy metal ions. Similarly to what we learned in Topic 6, an increase in temperature increases the rate of the reaction. It does this by increasing the frequency of collisions between enzyme molecules and substrate molecules that have energy greater than that of the activation energy. This, however, is only true to a certain extent. Above a specific temperature, known as the optimum temperature, the conformation of the enzyme changes by disrupting the bonds and forces responsible for holding its structure. The enzyme is no longer able to bind the substrate at the active site and it can't catalyze the reaction. This is known as denaturation. The pH of a solution influences the state of ionization of acidic or basic groups in the side chains of the proteins. However, the specific influence of pH on an enzyme depends on the R groups within the amino acids of the enzyme. The changes in ionization within the protein alter the forces stabilizing the enzyme, which affect its ability to recognize the substrate. Similarly to high temperatures, pH values differing from the range desired for the enzyme can also denature it. The optimum values of temperature and pH for an enzyme and substrate are maximally able to bind and form a complex. The final environment that can alter an enzyme is the presence of heavy metal ions. Elements such as lead, copper, mercury, and silver are poisonous to enzymes. When they are present as positive ions, they react with certain side chains on the protein, forming a covalent bond. This disrupts the folding of the protein and can change the shape of the active site and its ability to bind substrate.
created using Powtoon.